Hey guys, so let's finish off chapter 7, and we've been looking at the gas laws so far. We had looked at Boyle's law, which is the relationship between pressure and volume. We had looked at Charles' law, which is the relationship between volume and temperature. But with both of these laws, as we look at these parameters, we have to keep the other factors constant and prevent them from changing. So with Boyle's law, we're keeping the temperature constant, and we're keeping the number of moles of gas constant. With Charles' law, we're keeping the pressure constant and keeping the moles of gas constant. Now let's take a look at Gay-Lussac's law, which looks at the relationship between pressure and temperature. So as temperature increases, it gives the molecules more kinetic energy. The molecules with more kinetic energy are moving about faster, and colliding with the surface of the container more frequently. So as temperature increases, the pressure of the gas increases as well. So it's again like Charles' law. Gay-Lussac's law is a linear relationship. As the temperature doubles, the pressure would be expected to double. If the temperature was cut in half, the pressure would be expected to be cut in half. So the pressure divided by the temperature is equal to a constant value. If there is a change in the system, that change in the system means that the new pressure divided by the new temperature, P2 and T2, will still be equal to the same constant. So it gives us this idea that the initial pressure divided by the initial temperature in Kelvin will be equal to the final pressure, P2, divided by the final temperature. That is Gay-Lussac's law. Noble. Very interesting. Go. You're going to get popcorn with Mummy, yeah?
Yeah, but she's watching a different show. I want to watch Jurassic World.
Well, you can watch that with me later, okay? Later. So a graph of pressure against temperature in Kelvin would be a straight line graph. Doesn't want to watch the movie that Mummy picked out for tonight, apparently. Now, just like the other laws, Gay-Lussac's law depends on everything else being kept constant. So while we're looking at pressure and temperature, we've got to keep the number, excuse me, keep the number of moles of gas constant, and we've also got to keep the volume of the gas constant. If either of these two things change, then Gay-Lussac's law will not work. But let's look at some examples. Piston at 32 degrees, and it's exerting a pressure of 570 torr with the gas inside the piston. If the pressure was seen to increase to 1710, what must be the new temperature of the system? Well, we've got some conversions to do. Temperature has to be converted into Kelvin, as we said with Charles' law. So we add 273 to give us an initial temperature of 305 Kelvin. The pressure in torr, or millimeters, can be divided by the numbers of millimeters of pressure in an atmosphere, 760, to give us 0.75 atmospheres for the initial pressure, and then 2.25 atmospheres for the final pressure. So we plug in our values. Of course, the only thing we don't have is T2. So we want to move T2 into a place on its own. It's on the bottom, so as it moves across the equals, it'll move up to the top. P1 will take its place at the bottom, and T1 moves up to the top. So we get P2 multiplied by T1 divided by P1. We have got units of atmospheres for the pressure, but they will cancel out. we get a final value of 915 Kelvin. And because we desire the final answer to be in Celsius, subtract 273, and it gives us this value of 642 degrees Celsius. Even if we want the answer in Celsius, calculate in Kelvin. Oh, grammatically horrible there. Should be a capital C. With an S. I'm just used to using a C being British. Okay, there's the first one. We take a look at the second. Similar kind of problem. This time a container of nitrogen, and it's been cooled from 55 degrees down to 14 degrees over a 10-minute period. The initial pressure was 1.2 atmospheres. As the temperature cools to 14 degrees, what would be the new pressure? And give the answer in millimeters of mercury. Again, for the temperature, add 273 to convert it into Kelvin. So we've got P1 divided by T1 equal to P2 divided by T2. P2 is what we want to calculate. So we just need to move the T2 across the equals. It's on the bottom on one side, so it moves to the top to multiply with P1. So we get P1 times T2 divided by T1. The Kelvin units will cancel. It gives us 1.05 atmospheres. And we multiply by 760 the number of millimeters of mercury in an atmosphere to convert it into atmospheres, and a value of 798 millimeters of mercury pressure. Now, using Gay-Lussac's law, we can very nicely explain how surgical equipment can be sterilized, because boiling water gets rid of a lot of bacteria, but it doesn't get rid of all of it. We need to hit a temperature of 125 degrees Celsius for at least a 20 to 25 minute period. That will kill off all bacteria. But water just doesn't get hot enough because it boils at 100 degrees. So inside a steel canister, Gay-Lussac's law tells us if we increase the pressure, it will increase the temperature, and so we can hit the 125 degrees Celsius we're looking for. This is done while keeping the number of moles of gas constant and keeping the volume of the gas constant. Now, the last law we want to look at, or the last of the individual laws, is Avogadro's law. Avogadro's law looks at the relationship between the volume of a gas and the number of moles of gas. It's basically a direct relationship. You increase the number of gas molecules, you'll increase the volume, the space that that gas takes up. And so V1, the initial volume, divided by N1, the initial number of moles, is equal to V2 divided by N2, the final volume in molar amount. Again, we have to keep certain factors constant for Avogadro's law to work. This time we're keeping the pressure constant, and this time we're keeping the temperature constant. And quite often for these kinds of problems, we use a standard temperature and pressure known as STP, and that's a standard temperature of 0 degrees Celsius or 273 Kelvin, and a standard pressure of 1 atmosphere. Avogadro discovered that under these standard conditions, 1 mole of any gas, Avogadro's number of molecules, 6.022 times 10 to the power of 23, Avogadro's number of molecules, a mole, always occupies under standard conditions of temperature and pressure a volume of 22.4 litres. And we can use that as a standard if we're using standard conditions. 1 mole of any gas at STP 0 degrees Celsius in one atmosphere always occupies 22.4 litres. Again, let's look at some examples. And feel free to pause the video and try these ones for yourself before we move on and go over the answers. It's always good to get some practice. Okay, so let's take a look at these three for Avogadro's law. So we've got 60 grams of argon in a balloon that's inflated to a volume of 33.6 litres. If the volume of the balloon is reduced to 28 litres, how much argon gas is left in the balloon? So we start with our law for Avogadro's law, which is that V1 divided by N1 is equal to V2 divided by N2. But of course, we have got volume and the mass in grams, 60 grams. But Avogadro's law is about the number of moles compared to the volume. So we need to work out how many moles 60 grams is. So from the periodic table, the mass divided by the molar mass, which is 40, gives us 1.5 moles. Just use that molar mass. It's not like nitrogen or oxygen or hydrogen, which are diatomic gases and contain 2 moles of atoms. A mole of argon gas contains just 1 mole of argon atoms. It's inert, it's one of the noble gases, its shell is already complete. So it's not a diatomic substance. So we're ready for our calculation. Initial volume of 33.6 litres. Initial number of moles we worked out is 1.5 moles. And the volume, final volume is 28 litres. So as we just rearrange the equation to make N2 the subject, we're going to move N2 up to the top. So it's going to be end up on the top left. The 33.6 litres will switch places with N2 and move to the bottom on the right. And that 1.5, a divider on the bottom, becomes a multiplier on the top, so to speak, with the 28 litres. Okay. So if we fill in the blanks for that, oops, they're doing all of it. I had to go through all this. Hang on. I can always do it myself manually. My cutting pasting has failed to work. Okay. So let's set that up as it was. So we'll go N2. That's going to be the 28 litres multiplied by the 1.5 divided by the 33.6. And that comes to a value of, and so that comes to 1.25 moles. Now we multiply by the, excuse me, my goodness, multiply by the molar mass 40. And that tells us the mass for the 1.25 moles, which is 50 grams. So we've lost, from the original 60, we've lost 10 grams of the gas once the change took place. Let's look at the next one with the 5.6 litres of gas. Shouldn't have eaten those peanuts. So we've got 5.6 litres of gas at STP. Remember, that's standard temperature and pressure. And that tells us, under these standard conditions, 1 mole of any gas is equal to 22.4 litres. So we can use that volume, 22.4, as a measure of the number of moles under standard conditions. So we take the actual volume, 5.6 litres, and divide by the volume of a mole. It tells us how many moles we have. The 5.6 divided by 22.4, 0.25 moles. And so looking for the mass, that mass of nitrogen gas is 28 grams per mole, because nitrogen gas being N2, a diatomic gas. So 14 times 2, so 0.25 times the 28, that comes to 7 grams of nitrogen gas. Last one, similar to question 2, but just reversed around now. We've got a starting mass instead of a starting volume. So 132 grams. But how many moles is that? We can take our masses from the periodic table for carbon, 12 grams, and oxygen, 16 grams. So a mass of 1 mole of carbon dioxide is 44 grams. So the mass, 132, divided by the mass of 1 mole, it gives us 3 moles of gas. Now under standard temperature and pressure, STP, of course, 1 mole of any gas occupies 22.4 litres. So 3 moles must be 3 times the volume, which comes to 67.2 litres for the volume. Okay, that's Avogadro's law. And the only thing we've got left to finish off the chapter is to look at the ideal gas law. So of course the big problem with these gas laws is that we have to look at these individual laws while keeping other factors constant. However, if you take the pressure of a gas multiplied by its volume divided by the number of moles times the temperature in Kelvin, it always gives us a constant value. And this is like this X factor involved in gases when you're trying to manipulate pressure, volume, and temperature and the number of moles. This gas constant can be used to provide us with the ideal gas law, which is the pressure multiplied by the volume is equal to the number of moles times that gas constant, 0.0821 litres per atmosphere per mole per unit of Kelvin, multiplied by the temperature in Kelvin. This is the ideal gas law. PV equals nRT. And now that we've got a law that can be used for all of these factors together at once, we can use the ideal gas law and rearrange it, putting the variables on the left-hand side and the constants on the right next to the gas constant to work out the equation for any of the individual gas laws: Boyle's law, Charles' law, Lusac's law, and Avogadro's law. Let me show you what I mean. So if you had a question which said that you had a balloon with 0.5 litres of air at 25 degrees Celsius and it was cooled to 5 degrees Celsius and you were asked to calculate the new volume, maybe you'd be a bit rusty, or maybe you would be unable to remember what the gas law looked like to handle pressure and volume. Sorry, pressure and temperature, I beg your pardon. But we can use the ideal gas law equation to work it out. Remember, keep the variables that you're going to work with on the left and the constants on the right. So we've got changing volume, we've got changing temperature. So as we look at the equation, the pressure needs to be moved across to the right. We're not looking at pressure with this problem. It's one of the constants, like the gas constant. Now, because as it moves across the equals, instead of a multiplier, it becomes a divider. The other thing we need to move is temperature. That's one of the parameters that we are looking at. It is a variable because we're going from 25 degrees down to 5 degrees. So we need to get it from the right onto the left, away from our constants. And as the temperature moves across to the left, it becomes a divider. So we get the volume divided by temperature is equal to nR divided by P. These are the three factors which are constant. And so we've given ourselves Charles' law. Volume divided by temperature is equal to a constant. And so the final volume divided by the final temperature, V2 and T2, will also be equal to that same constant, nR divided by P. So rearranging the ideal gas law to have the variables on the left and the constants on the right gives us the gas law that we're looking for. Let's take a look at a couple of others. And again, you can pause the video for a second before we take a look at these and work this out for yourself. So let's take a look at an example. And we're going to use the ideal gas law to work out how to perform the calculation. So a gas with a measured temperature of 16 degrees and the pressure is increased from 380 to 1140 torr. What would be the calculated final temperature? So let's start with the ideal gas law. That's not the ideal gas law, I beg your pardon. There we go. So PV is equal to nRT, and we want to rearrange the equation to put the variables on the left and the constants on the right. So pressure is where we want it to be on the left because pressure is going to change, but volume is not. We have to get rid of the volume and move it to the right hand side, or temperature, another one of our variables, has to move over to the left. So we get the pressure divided by temperature is equal to nR divided by V. These are our three constants. And that's very much looking like Gay-Lussac's law. Pressure divided by temperature is equal to the final pressure divided by the final temperature, P2 and T2. So we've got some conversions to make for our problem. 16 degrees plus 273 gives us 289 Kelvin. 380 torr divided by 760, the number of torr in 1 atmosphere, gives us 0.5 atmospheres, and 1140 torr divided by 760 gives us 1.5 atmospheres. So conversion's done. We can set up our calculation. P1 over T1 equals to P2 over T2. The only thing we don't know is T2, so we can rearrange. We get 289 Kelvin times that 1.5 atmospheres of pressure divided by 1 atmosphere. There are a final temperature of 867 Kelvin, or subtract 273 to give us 594 degrees Celsius. Let's take a look at the second one. So we have a gas with a volume of 800 milliliters at a temperature of 24 degrees. If the pressure decreased from 2.5 atmospheres down to 1 atmosphere, while the temperature remained constant, what would be the new volume of the gas? So we've got pressure changing, we've got volume changing, so that means we've got Boyle's law. Look at the ideal gas law. We're already set up for Boyle's law. Pressure and volume are on the left where we want them to be, and our constants, the moles, the gas law constant, and temperature are on the right. So P1V1 equals P2 V2. We can plug in the values that we have. And so the only thing we don't know, of course, is that final volume. Rearranged to make volume the subject of the equation. We get 2.5 multiplied by 0.8 divided by 1. So that final volume would be 2 liters. Let's try the third problem. So a balloon of oxygen with a volume of 134.4 liters, weighing 192 grams. What would be the new mass of the balloon if the volume was decreased to 100.8 liters? What would be the volume of 192 grams of oxygen gas? So we're looking at changing volume and a changing mass of gas. And of course, that changing mass is synonymous with a change in the number of moles. So the question is really about the volume in moles, which is a question about Avogadro's law. So we can use the ideal gas law equation to move our variables to the left. The volume is already on the left where we want it, but the pressure is going to be a constant. So that has to move to the right. The number of moles is changing, so that has to move to the left. So we get the initial volume divided by the initial number of moles is equal to R multiplied by T divided by P, which is going to be a constant. This is Avogadro's law. So we need to turn that mass of oxygen into a number of moles by taking the mass and dividing by the mass of 1 mole. 32 grams for oxygen. It's a diatomic gas after all. And that gives us 6 moles. So for our calculation, V1 divided by N1 equal to V2 divided by N2, we can rearrange to make N1 the subject of the equation. And that's going to be V2 times N1 divided by V1. We can plug in our values, 100.8 liters for the volume times 6 moles divided by that volume of 134.4 liters. That comes to 4.5 moles multiplied by the mass of a mole, 32 grams for oxygen gas. That gives us a mass of 144 grams of oxygen gas. Okay, that is the end of the chapter. And then our final moment of Zen, which is probably my favorite, this one. Can you work out what the problem is? Okay, remember you've got your Chem Talk videos for chapter 7 as well, and also the question of the day videos. There are at least 3 of them. And we'll have the exam for the chapter 7 at the end of this week. No break before the next exam. We're straight into chapter 7 this week.